All right, so now I want to show you two other sorts of line integrals and practice computing them. So notice that these two line integrals that I have here look different from the one we were just talking about in the previous video because we don't have a ds differential unit in them. Instead, we have a dx or a dy. So the context is still the same. We're integrating under a two-variable function over a parametrized curve, and the dx differential and dy differential in that case, when you have a parametric curve x of t, y of t, dx, for example, is then just x prime of t dt, and dy is y prime of t dt. So these line integrals, these are called line integrals of fxy with respect to x or with respect to y, as opposed to with respect to arc length. These do not measure that curtain-like area that we were talking about earlier, but these end up being fundamental components of lots of other integral structures that we're going to study in this section. So let's practice computing them. If I have the integral of this, I'm understanding this to be a two-variable function, fxy is y squared, with respect to x over this curve C1, then this is how we compute it. We start, as before, parametrizing the curve. And this is a nice little trick for parametrizing a line segment. If you write your starting point and ending point as vectors, and then in front of the starting point, put a 1 minus t, and in front of the ending point, put a t, and then run t from 0 to 1, that will parameterize your line segment in 1 second from t equals 0 to 1. You can see when t equals 0, you're at the first point, and when t equals 1, this is 0, and you're at the second point. So let me go ahead and get the components of this vector function in terms of x and y. Okay, so this is my x of t, this is my y of t, and my t ranges from 0 to 1. That's the parameterization of the line segment. So remember that trick anytime you want to parameterize a line segment, either in 2 dimensions like this, you could do the same trick in 3 dimensions. Okay, now for the dx. dx, remember, is x prime of t dt, so that's just 5 dt, and I've got everything I need to set up my integral. Okay, as you can see here, I've written y squared, the integrand, in terms of the parameterization, and then this right here was my dx. Now I just have a Calc 1 integral to solve. Okay, there you go. Whatever that is the value of this line integral with respect to x. So distinguish these line integrals in your mind. We've got line integrals with respect to arc length. This one is a line integral with respect to the x variable. You could also compute an line integral with respect to the y variable as well. Let's just, for practice and parameterization, evaluate the same integrand with respect to x across a different curve, this time a parabola that connects this point to that point. Okay, in order to parameterize this, I'm going to go ahead and let y be the parameter t. It starts down here at -3 and goes up here to 2, because I can see that x is a function of y, and that'll make it convenient for y to be the parameter. Okay, and as before, dx is x prime of t dt, and I'm ready to set up my integral. As before, we have our y squared here in the integrand, and then this is our dx, and our parameter goes from -3 to 2. Just remember that the y is the parameter t. That's how I set it up. Okay, and there you have it.